Good afternoon. My name is Dwayne Brown with the Office of Communications, and welcome to NASA headquarters. Today, you will hear the latest update on the largest and most capable robotic machine going to the surface of another planet. NASA's Mars Science Laboratory, otherwise known as MSL, scheduled to launch from the Florida Space Coast this month, and you'll hear the latest details on that. Information about this incredible mission is on www.nasa.gov/MSL, and the press kit that has all of the detailed information on the mission and all of the other logistics is at http://go.nasa.gov/MSL press kit, all one word. We'll have short presentations from our speakers, then we'll open it up for questions starting here in Washington, our NASA centers, and the phone lines. Before we get started, let me introduce you to today's speakers. First up, Doug McCuistion, Director, Mars Exploration Program, NASA headquarters in Washington. Ashwin Vasavada, Ashwin Vasavada, MSL, Deputy Project Scientist at NASA's Jet Propulsion Laboratory, Pasadena, California. And Pete Tysinger, MSL Project Manager, also at the Jet Propulsion Lab. And with that, I'll toss it to Doug to kick us off.
Thanks, Dwayne. Boy, it's great to be here. It's a momentous occasion, but of course, what's really important is, the last time I sat at a press conference on MSL, it was to announce a slip. This is where we really want to be, and it's fantastic to be here. I am very proud to say that MSL has been assembled, tested, encapsulated, and stacked on top of the Atlas, and is ready to go. 15 days to launch. Pretty incredible. It's not your father's Rover. This is a 2,000-pound machine that's over 6 feet tall. It's truly, as Dwayne said, the largest and most complex piece of equipment ever placed on the surface of another planet. Truly a wonder in engineering. From Long Island to California, from New York to Florida, we've employed thousands of people in very high-tech careers for the last 6 or 7 years on this mission, and that's going to continue as we cruise to the planet and actually get to the surface and operate and do wonderful science. It's the best of U.S. imagination, the best of U.S. innovation, and we couldn't just do this alone. We have a lot of partners with us. We have France with us, we have Canada, we have Germany, we have Russia, and we have Spain. In the U.S., of course, to launch this, we have United Launch Alliance and the Kennedy Space Center and the United States Air Force of Cape Canaveral, and of course we have the Department of Energy aboard. So it's truly a spectacular mission with a lot of involvement worldwide. Can we have the first graphic, please? What you're looking at is a strategic, integrated program of Mars exploration. We began this program back in roughly in 2000. You'll see the operational missions there still include Odyssey and MRO. Of course, the Rover Opportunity is still operating. We have a partnership on Mars Express. Phoenix we flew in 2007. But MSL sits squarely in the middle of this strategic two-decade-long activity. And what it does is it bridges the gap from the past decade, scientifically, to the next decade, and technologically. Scientifically, from understanding the planet as being warmer and wetter than we had previously believed, to the next decade to try to understand if it was ever habitable, and potentially even seeking signs of life, not life itself. It's not a life detection mission. Technologically, we move from airbag landings and small systems of a few kilograms of payload to much larger systems and putting that 2,000-pound rover on the surface. So MSL is pioneering the challenges of high technology. We have ever-increasing payloads. We've got more accurate landing capabilities. We've got longer-lived systems on the surface with nuclear power, and we have state-of-the-art instruments aboard. These are also techniques that are necessary as we move towards the ultimate goal of putting humans on the surface of Mars. An extremely exciting time for the Mars program and for NASA. This is the capstone of the year of the solar system. The science that we'll be doing that you'll hear about from Ashwin, we couldn't even dreamed of doing 10 years ago at this scale. And technology as well. We've moved from Pathfinder to Spirit Opportunity to MSL, and you'll hear more about the technologies from Pete here shortly. But it's really pretty amazing how in a matter of 15 years we've gone this far. And again, we bridged the gap from follow the water to seeking the signs of life. We'll excite the nation, we'll inspire the nation. We're going to show incredible new vistas, great new discoveries, but most important is the launch is just the beginning. We still have a little bit of cruise, but then the key is landing in August of next year, and that's going to be exciting. It's very challenging, never done it this way before, but you'll hear about that from Pete, but we're just thrilled that we're at this point. So what I'm going to do is turn it over to Ashwa and let him talk to you about the science.
All right. So as a scientist on this project, I can tell you that this is a Mars scientist's dream machine. We're so excited to have this rover go into Mars this year. It's going to be the virtual presence for over 200 scientists around the world to explore Mars and Gale Crater that we'll talk about. This rover is not only the most technically capable rover ever sent to another planet, but it's actually the most capable scientific explorer we've ever sent out. And so with that, we're just super excited. It's about twice the size of previous rovers, has 10 very capable scientific instruments. And on the first graphic here, you can see that the rover, like previous rovers, has 6 wheels. It is much bigger, though. It's about 6 feet tall. And what really dominates the design of this rover is the fact that it has this ability to sample rocks and soils on Mars for the first time. And so it has a big 6-foot robotic arm. And the rover is partly that big because it holds 2 very capable scientific laboratories inside the rover. So one of the things that the rover does is to survey the landscape around Gale Crater. So it does that with some HD cameras. It also has that eye on the top of the rover, which shoots out a laser and can survey the chemical composition within 20 feet of the rover. Then another thing we do is monitor the environment. So we have a very capable weather station for winds and pressure, humidity, that sort of thing. We can sound below the rover to figure out if there's any minerals that contain water below the rover. We also detect natural high-energy radiation. This kind of radiation is critical to measure for the day that we do send humans to Mars. And in fact, this sensor is being flown by the human exploration part of NASA. On the next graphic, you'll see what really is the meat and potatoes of this mission. When we deploy that arm and we put out a whole bunch of sensors on rocks or soils that are of interest to the science team. We have some tools here where we look close up with a magnifying glass camera. We also have another sensor on the arm which takes an even more detailed chemical look at the composition of the rocks and soils. But the crowning achievement scientifically of this rover and technically is to drill into rocks and capture material from the insides of rocks, which we've never done before on Mars. And that's really where the science will come from. And we drill in with a big jackhammer drill. We deliver that sample to the rover itself and analyze it with 2 very sophisticated instruments, one of which measures the minerals that are in those rocks and soils, another which looks element by element, which chemical elements are there, and looks for any organic material that might be present. But before we can do any of this incredible science, and really it wouldn't be worth doing if we didn't have a spectacular landing site as well. And so the next graphic shows a really nice image of the sun rising over Mars. And you can see the cratered southern highlands in the near part of the picture, the smooth plains in the far part. And right on that boundary, in the middle of the image here, there's a crater with a mountain inside of it. And that mountain inside the crater is what caught the eye of the scientists that have been studying Mars for the last decade and resulted in it being chosen for this mission. If you go to the next graphic, you'll see that Gale Crater is about 100 miles across. That yellow ellipse is where we will land Curiosity, and then we'll drive towards the mound. The mound itself is over 3 miles high. And on the next graphic, I'll tell you a little bit about why this mound is so spectacular scientifically. It's actually composed of layered rock, and we see that from the orbiters that are around Mars now mapping the planet. We've discovered that the layers are flat, which means probably sediment at one point filled the entire crater, and now it's been stripped away. But even more interestingly, the layers are made up of different material. The bottom layers are a mixture of clays and sulfates. Then you go into layers that are just sulfate salts. And then you get into some upper layers, which are just, frankly, uninteresting Martian dust. And it's that change over time, which the whole planet has experienced. But what's incredible about Gale is it's all in one place here. Probably the entire early history of Mars is here for us to drive out of that ellipse over several months and then start climbing this mountain with Curiosity. So we couldn't be more excited about that. And before we do any of this, we got to get there. And so that's what Pete Tyson will talk with you about.
Thank you, Ashwin. As Doug mentioned, we are in Florida. We are prepared on the vehicle and prepared to go. I want to show some pictures of the buildup of the vehicle. Um, when you land on Mars, when you go to land on Mars, what you're really talking about is 3 vehicles, not just one. There is the vehicle that gets you to Mars. There is the vehicle that actually penetrates the atmosphere and goes through the entry, descent, and landing portion of the mission. And then there is the rover that eventually gets deposited on the surface. And I'll show you some pictures of how we build up that vehicle in that way. The first graphic is the rover itself. You can see, as Ashwin mentioned, it's a 6-wheel, what we call rocket bogie system. You can see the arm on the left with a turret assembly, which has several of the science instruments. And you can just barely make out in this photograph the mast above. As Doug mentioned, it's about 900 kilograms, roughly 2,000 pounds. If I could have the next graphic, please. Um, as Doug mentioned, this requires a new and novel system in order to get to Mars. We're not landing like Mir did on the airbags. We are landing propulsive like Phoenix, but we're landing a rover, and it's not a stationary lander. And so what you see on the graphic is the descent stage that we use to propulsively lower the rover and itself to the surface of Mars. You can see the 8 large main landing engines, and then off to the right, that large kind of surfboard-shaped feature is the landing radar, which you use to measure the velocity that we land at and the altitude, both very critical for this particular landing system. If I could have the next graphic, please. This shows the rover underneath that descent stage. You can see the reddish elements are protective covers around the main landing engines. They're used when we put assembling things so that they don't get damaged. And you can see that the composite of that, the descent stage plus the rover, is being put up inside the back shell. That's the top half of the entry vehicle. If I could have the next graphic, please. And now you see that assemblage is now up inside the white back shell, and below it is the heat shield. Looks very much like an Apollo entry capsule, except in fact it is larger than an Apollo entry capsule. It is about 4.5 meters across at the bottom. If I could have the next graphic. This is the entire vehicle that goes to Mars. The part at the top, which has the white circumferential banding, is the crew stage. That is all the equipment that we need to get to Mars, but we don't need at Mars. It includes telecommunications equipment, the solar arrays for the interplanetary transverse, and the propulsion system to do the trajectory connection maneuvers in order to get us navigated to the right place for entry. When we launch, this is actually upside down. We actually launch with the heat shield up and the cruise stage down on top of the Atlas. Next, please. And here you can see kind of the last picture of the vehicle as we could see it as a total vehicle before it was encapsulated in the fairing. That shows the Atlas fairing, which is then put around the vehicle. And then the fairing plus the vehicle is transported to the vehicle integration facility at the launch pad. If I can see the next graphic, please. This shows the vehicle inside the fairing being lifted to the top of the Atlas. I think that occurred on the 2nd of November. And if I can see the next graphic, please. That shows the assembled vehicle as it currently is. We're going through final launch vehicle operations, and we're going through final electrical testing inside the rover. And we'll be all prepared to launch on the 25th of November, the Friday after Thanksgiving. Of course, once we launch the vehicle to Mars, that is only the first part of the journey in order to get Ashwin science instruments to a place where he can do science. And I'll show you an animation now of the kind of the total mission in 2 minutes. So bear with us. We could start that, please. We inject on the Centaur upper stage, and we are kicked off on the cruise trajectory. It takes 8.5 months for us to get to Mars. We are a slow spinner, and that traverse. We arrive at Mars doing about 12,000 miles an hour. We kick off the cruise stage, and we enter the atmosphere. You can see the thrusting of thrusters that we use to do the precision landing that both Doug indicated and Ashwin showed the landing ellipse. At 2,000 miles an hour, Mach 2, about 1,000 miles an hour, we kick out the parachute, drop off the heat shield at about 10 kilometers high, and then about 2 kilometers high, we drop off the descent stage and propulsively lower ourselves toward the planet. When we're a couple hundred meters off the ground, we actually lower the rover on what's called the sky crane, and cut the bridle, and then the descent stage flies away, and we have the rover sitting on its 6 wheels on the surface. We will then either do in situ science if we happen to land somewhere exciting, or we will traverse to a interesting science site. And you'll see here going up to an outcrop, deploying the arm, which contains the drill, which we use to collect samples, showing the depositing of that sample in one of the science instruments for its analysis. It's a very complicated rover. We will take our time when we get to the surface. The initial science will probably not be coming very fast. It will take a lot of how good is the rover in its condition, what's the science terrain like, where are the closest science targets, how does the drill really work on Mars? Very difficult to test that on Earth. So it'll be a while to get the first real samples back, but it's a 2-year-long mission, and we're expecting tremendous results. Entry, descent, and landing is always an exciting time and a challenging time. We're confident in our ability to do it successfully at the planet, but it is clearly not risk-free, as you can see from the complexity in the animation. Dwayne.
Okay, thank you, gentlemen. Okay, what we're going to do is actually we're going to go down to the Kennedy Space Center where they're preparing for the launch and hopefully preparing for a deluge of folks for Thanksgiving dinner there. So Kennedy Space Center, you're up first at bat, and let's have the first question, please.
Hello, this is Marcia Dunn of the Associated Press. I'm wondering, could you give a list of some specific signs of life you might be looking for with the rover, and why not? Why didn't you just put some life detecting equipment on board to actually look for real signs of life?
Sure, I can answer that. It's important to know that this mission is really has a purpose of setting us up for the day when we'll go to Mars and do the life detection experiments. It turns out those are pretty hard to do, and you actually need to know a lot about Mars to understand where to go to do those experiments. So the goal of this, as Doug mentioned, is to look for habitable environments on Mars. These would be environments that are capable of supporting life. We actually are pretty limited in our knowledge of where to look for those. We have Gale Crater, which is a very promising site, because it has some things we can detect from orbit that would indicate a habitable environment. For example, it has some geologic evidence that water was around. We hope, in fact, to search for organics with this mission. That's another requirement for life as we know it. But this mission is really about looking for those habitable environments and not detecting life itself.
Another question from Kennedy?
Thank you. And how might this rover pave the way for future human explorers? How might it make life easier for them?
That's a very good question. Many of the things that you need for humans to explore the planet involve, obviously, as Pete was talking about, landing. That's very complicated. So we are shrinking landing ellipses dramatically from 100 kilometers or so down to a small circle of about 20. So that type of precision landing is a direct precursor. The ability to manipulate and handle samples robotically on the surface, in other words, all the sample handling that needs to be done to get samples into Ashwin's instruments, is also something that would be useful in getting humans to Mars. Larger masses to the surface, you have to resupply astronauts on the surface as well as feed them and water and other kinds of supplies. And so this is a good landing system to do that type of thing. And just learning how to get through the atmosphere with much larger masses will take us to humans. Now, Ashwin mentioned a specific instrument is called RAD, which is a radiation detector provided by the Human Exploration Organization at NASA. That actually is the first time we've taken measurements on the surface in great detail over several Earth years and maybe several Martian years if we're lucky. And that is obviously going directly into the database to understand how much radiation would astronauts be exposed to on the surface over time, and then how you can actually mitigate some of those effects. So those are just a few of the issues that could help with humans to Mars.
And before we take the next question at Kennedy, just a note for the media watching this and here. The Kennedy Space Center will be issuing a media advisory, if they haven't already, that pretty much lays out a virtual buffet of diverse briefings that talk about Mars, getting into the specifics of the science, and also a press briefing from the Johnson Space Center on the human future human exploration and the synergy between robotics and human exploration. So stay tuned for that briefing. And on the website, www.nasa.gov/MSL, you'll also see that coming out of the Kennedy Space Center and NASA headquarters. Next question from Kennedy, please.
Thanks. This is Todd Halverson of Florida Today for Doug. Doug, could you update us on negotiations with the Europeans in regard to the 2016 mission, what the split of responsibilities would be, and whether you guys are going to actually have the money to do it and be able to come to an agreement with the Europeans?
Todd, I'd like to keep this focused on MSL, but I'll give you a couple of second answer here. We certainly have continued, obviously, our work with the Europeans. Obviously, the U.S. and ESA realize we may have some budget concerns in the future, and so ESA has approached Russia about potentially providing a launch vehicle and maybe be involved. At this point, since the 2012 budget isn't passed, the 2013 budget is still in development, I really can't talk about the budgets any further than that. So I'd kind of like to leave it at that, Todd, and in a few months I think we'll have more that we can share. And so, Dwayne, I'd kind of like to keep it on MSL, if you don't mind.
Roger that. Kennedy, any other questions on MSL?
Yeah, I won't ask about America's future programs at Mars, then. We'll just stick with MSL. I'm wondering, the Skycrane entry and landing scheme is quite different from anything you've ever done before, and to a lot of us, at least sitting on the sidelines, it seems to be, scary. I'm wondering if you can kind of describe or compare it to some kind of mechanism on Earth, and exactly, whether you're going to be biting your nails during that descent and entry.
Well, I think any entry, descent, and landing on Mars is a place where you take pause and bite your nails a little bit. It's not a risk-free environment. When the agency decided the objectives for this mission and the suite of instruments that would be required to perform the science, and we saw that we had to develop a very large rover, it was very clear that that was beyond the scale of airbags to be able to land successfully. And so we had to land in a propulsive way on the planet. And if you think about it, there's only two ways to land the rover propulsively on the planet. That's to put the rover on top of the propulsion system or put the rover under the propulsion system. If we put the rover on top of the propulsion system, kind of a traditional way that you've seen, it looks, without a rover, but you've seen Viking and then Phoenix, you've got to get a 2,000-pound rover off the top. And that was a daunting thing to do. In examining this, we said, well, we already have a system that's capable of contacting the surface and interacting with the surface, a landing gear, as it will. That's the six-wheel rocker bogie system. So the challenge is really to just simply, I shouldn't say simply, is to put it there softly enough, in a controlled enough fashion. And I don't want to say that we looked at this flippantly, because there were an awful lot of people that had exactly your same reaction of, you've got to be kidding. But we did an awful lot of independent reviews. We went to an awful lot of non-NASA control specialists, the people who actually fly helicopter Skycranes. We got them in the game to talk about whether or not this was not only an achievable design system, but whether or not we could put together a test program that would verify it adequately enough. And we convinced ourselves, and were reviewed several times by the agency, that we were able to do that. And so that's the system that we've put together. We have done a tremendous amount of entry, descent, and landing reviews and tests. You can't do the test in an end-to-end sense, because you can't land on Mars, on the Earth, but you can do the test in a piecewise sense. So we have done deployments of the Skycrane with test equipment, and we have done surface contact testing to do the landing. We have done radar testing on helicopters and F-18 jets out at Dryden to basically test all the components of the Skycrane system. So we're confident that we've done our due diligence, and Mars may interfere with us, but or there may be something we haven't caught. That's always the element of risk. But to the extent that we've been able to think of it, we've attacked all the problems and done all the testing we can do.
And before we go to Kennedy again, just a reminder, we do have briefings that will start on November 21, a whole series of briefings. So we're going to keep this briefing, and we have a limited time to MSL questions only. And if there are other questions on other related topics, please contact 202-358-1726, my office, and we can get you the appropriate folks. So Kennedy, another question, please.
Hi, Dan Billow from WESH-TV. Would you talk a little bit about an extended mission? How long do you think that this rover could last? And I may have missed it, but would you talk a little bit about its speed on the planet? How much faster, if any faster, can it go over the planet's surface than the other rovers?
Its speed is about 1/10 of a mile an hour, which is about the same as the Mars Exploration Rover. We should be able to do better in terms of a daily, how far can we go in a given day, for two reasons. One, we're basically limited for safe driving on how far ahead we can see reliably. And the rover, since it's taller, will give us a better vision in that standpoint. Also, an advantage that we have now that we didn't have with the Mars Exploration Rover, benefit of the Mars program, is we have Mars Reconnaissance Orbiter in place, and the HiRISE instrument is able to do 30-centimeter photography of the surface and has extensively covered our landing site and will continue to do so. So we'll be able to basically lay out the track far ahead for our daily traverses with looking at rocks that with good enough resolution so we could see things that might get in our way. And so that's a diverse question. Oh, a lifetime question. Well, I'm the project manager, so my warranty expires at the day after the level 1 requirements. But we do test all the mechanism equipment for 3 times its normal life. There is no life-limiting consumable per se on the design. The power source will last a great number of years. We will not have the dust issues that we had with MER. We'll be able to handle winter a lot better than we are on MER. So on the face, there's nothing, bearing wear out, and that could be any time you want to figure. We should be good for quite an extended period of time.
Okay, I see a couple of folks here in the audience in our studio, so if you give your name and affiliation, thank you.
I'm Joe Palka from NPR, and I've got a question for Ashwan, a question for Pete. You want me to do them serially or in parallel?
Whatever works for you.
Okay, well, I'll start with Ashwan. In the last set of missions, we were waiting for signs of water, and there were press conferences when we saw some chemical reaction that gave us a sense of we finding it. In this mission, I know you don't know what you're going to find till you get there, but what kinds of things would be, oh, this is worth a press conference because we found X?
Well, as Doug was mentioning, that the program's kind of transitioned from following the water, and these, as you mentioned, the rovers that are currently on Mars, Opportunity, Spirit, they both found evidence for water in different forms. Water that has interacted with the soil and formed minerals that require water, evidence for actually flowing water on the surface. So that is sort of in the rearview mirror now, and we've moved on to this evidence of habitable environments. So the kind of things that would, I think, generate excitement for us is really confirming, first of all, confirming what we saw from orbit. So there's evidence from orbit for these clay minerals, and the clay minerals in particular are fascinating because they do require water, a lot of water, to interact with rock over some time to form these minerals. And it's done through spectroscopy from orbit. There could be some errors, there could be some things we don't understand about the data, but we will have a definitive knowledge of the minerals with this rover. So understanding that clay environment and actually trying to figure out what sort of the rest of the environmental conditions on Mars were that caused that clay to form, what the weather was like 3 billion years ago, what the temperatures were like, and that gets at this whole issue of creating a habitable environment. So, we can't wait to drive across the ellipse over several months and get to that first clay outcrop. And then we'd go up the hill and look at the sulfate salt area, which should represent a different environment. And so I think, we have a lot of steps that we'll go through. Really, we're reading the history of early Mars in several different environments. And if any of those look definitive, no, I don't know, I won't say definitively, but if any of those really scream out that this was a potentially habitable environment, we'd tell you.
And Joe, you have another
question? Yeah, well, for Pete, in my experience with engineers, they always have a list going somewhere in their heads of the things they're most concerned about. I'm wondering what things are at the top of your list in terms of what you're concerned about. And also, in the MER experience, there was a lot of testing and getting ready right through the cruise stage because the timeline was such that there was still a lot to go. Now, you had 2 years extra on this mission, so maybe you're not quite as up against it with some of the software, but I wonder if you could talk about what's at the top of your concern list, and will you be doing additional testing of equipment on the cruise phase?
I think the thing at the top of my concern list is what I don't know. You know, these things are very complicated beasts, and you test the heck out of them, but you can't test all their interactions. You can't test them for the length of time of the mission. You just can't do all that kind of intensive things. And so there's always going to be surprises. Sometimes engineers call them features. And what you worry about is that there's something there that's really serious. You know, when MER launched, we had done what we thought was a comprehensive test program, but we had 4 surprises after we launched that we had to fix operationally, and we were able to do that. That's what you worry about, that there's something in the design that you haven't caught yet, that's something in the interaction with the Mars environment that you're not able to test on Earth, that there's something in long duration exposure that you're not able to do, that something like that will catch you. And it'll be a software thing more than likely. That's what you worry about more than anything else. You asked the second question, and I...
Cruise?
Yeah, well, it would be nice to be say that the 2 years allowed us to be completely done on the Friday after Thanksgiving, but that's not true. We have a lot of work to do to characterize the sample handling and sample processing system, as Ashwin pointed out. One of the things we've discovered in the last year of testing is the interaction with the rock systems, with the rocks, very dependent on temperature, very dependent on pressure, very dependent on the composition of the rocks. So we're laying out a very comprehensive test program to basically lay out for us what are going to be the operational rules of the road and as we interact with rocks, what will we have to do do first-time activities, what we say, and to be able to do those things. So that's a test program that we've got laid out. We will continue to do development for entry-descent landing in the sense of running the software again and again and again, and testing all the corners of the environmental box to make sure that you're very robust in terms of what Mars could throw at us from an atmosphere or dust storm sense. We don't expect dust storms. We're in the wrong season, but we'd like to be prepared for everything. And then we've got some software development for the surface mission to engage in. So we're a little bit thankful. MER was a 7-month cruise. We're thankful we have 8.5. We'll use it all. But we will be busy over the cruise period for sure.
Okay, now we're going to transition to the telephone lines, and we're going to wrap up after the phone lines, but let's see if we can take a few questions there. And I believe first up is Irene Klutz from Reuters. Irene, are you there?
Yes, thanks, Dwayne. I have 2 questions. The first, I think that there was another instrument added with the delay in the Mars Science Lab launch that actually was very much targeted to looking at the types of organics, if any, are found, which is maybe a little closer than what you've described so far as being able to assess life. Can you talk about that a little bit? And then I do have a related question. Thanks.
Sure. There is one of the real cornerstone laboratories that it's located inside the rover has been with the mission since its inception. In fact, the mission was really designed partially around, the rover was really designed around this instrument. It's the workhorse laboratory. It's called SAM, Sample Analysis at Mars. And it's a suite of instruments that analyzes that powdered rock or soil sample and even the air as well, and looks element by element what the composition is, and it also has the capability to detect any organic material that's in the rocks or soil. Now, we consider that kind of a science home run. That sort of gets at Joe's question too. That is something, you know, that would make the papers, but we're also not banking the mission on that. We don't know if Mars has the ability to retain any organic material, even if it's there. So part of this mission also is understanding, you know, now looking at ancient Mars 3 billion years later, what sorts of evidence does Mars preserve for us to study today from when it was probably more habitable in the past? So we do have a fabulous organics detection capability on the rover, and if we find something, it's a home run.
Our next caller is Clara Moskowitz from.
Thanks very much. And I think the other question's for Doug. Has Russia requested any assistance from NASA in trying to track or do anything to recover the Phobos grunt mission?
We have offered assistance, and if they need it, we will provide to the best of our ability with our space communications network. That's a different organization than ours. I'm not sure if they've asked for the assistance, but we have offered it.
Okay, thank you, and I apologize, Irene, that you had a follow-up. Okay, now we can go to Clara Moskowitz from Space.com. Clara?
Yes, hi. This is a question for anybody who wants to take it. Based on all you know right now, just how likely do you think it is that you're going to find evidence that Mars was habitable, and just how likely is it that you think Mars ever had life?
I'm not sure that any of us want to take that. You can add to this.
Okay, sure.
That's kind of a request for speculation, and I really kind of hate to do that. Let's take MER as an example. Nobody would have expected to see the blueberries that we see by the millions, and that was a huge discovery. Mars Reconnaissance Orbiter has found evidence in mid-latitudes, actually a little higher latitudes than we'd ever thought, of briny waters that could actually be liquid on the surface for short periods in certain seasons. So every time you turn around, there's something that Mars does for us or shows us or reluctantly hands to us that maybe we're looking for it and maybe we're not looking for it, but it's always exciting and it always feeds the science. So I really don't want to speculate on how likely it is that we'll find these things, because we may not find those, we may find something completely different. So it's a little tough to speculate. So now I'll let our scientists speculate for just a second.
The first thing I'll do is clarify for the people new to Mars exploration that we didn't find blueberries on Mars.
Yes, thank you.
Yeah.
That's true.
Yeah, those are hematite crystals, but they're fabulous things. But I'll just say, I was going to say the same thing as the caveat, which that would be sort of in the realm of speculation. But on the positive side, the reason we're excited about Mars exploration and going to Gale Crater is that when we look in the distant past, sort of the early 1 billion or 2 years of Mars history, we've known now for decades that there's evidence for rivers flowing and possible lakes, even a possible evidence of a lake in the crater we're going to. We're not sure about that, but that's why we're going there. We're trying to find out if there were these habitable environments which would involve liquid water. And so, we're targeting, I guess the best way to say it is, through the science community, through hundreds of scientists that have helped select this landing site, we've chosen the best possible place to discover a potentially habitable environment, and we'll see if we find one.
Oh, but we find blueberries with MSL. I can write the press release.
There you go.
Okay. Like that. All right, next caller, Dan Leone from Space News. Dan,
Right here, thanks. Question for anybody who wants to tackle it. We know that the planetary science budget was going to go down anyway, and now we know to save James Webb it's going to go down a little bit more. What contingency plans, if any, have you made to support the primary MSL science objectives in the likely situation that the budget for this division is going to fall off a cliff a little bit next year? Anybody who'd like to take it?
Yeah, I'll take that. MSL is an incredibly important flagship mission for this agency. We've been in the build and test phase for years. It is that bridge mission, and it's as important to this agency, I would, personal opinion, a little biased maybe, as Hubble. The funding for MSL is stable. The agency, PMC, the administrator, has signed the current budget estimates that we've got for it. That money is set aside. If there are funding reductions in the 2012 budget, once it gets passed by Congress and in the current budget uncertainties, who knows? But if there are, the MSL operations funding is safe.
okay, we have time for a couple of more questions from our phone lines, and then we'll take one last question from our studio audience. Let's go to Raphael Jaffer, and I'm sorry, I'm having problems with names today. Jaffe. Mr. Jaffe, aerotech.news.
But if there are, the funding is there.
Raphael, are you there?
We have time for a couple.
Okay, all right. I'll tell you what, let's see if we can come back here to. Go ahead.
Sorry. Kitty Feldy with KPCC Public Radio in Los Angeles. Could you talk a little bit about the propulsion system, since you're not using the solar panels that the earlier rovers had used? Because if you say nuclear, people seem to have a problem with that. Can you talk about the safety issues of launching nuclear fuel into space?
Well, let's see. We're using the power sources of a multi-mission radioisotopic thermal generator. It uses plutonium dioxide in sinter cylinders and then bricks inside of a cylinder in order to generate electricity using thermocouples. It's a direct heritage of designs for such generators that have been used on a lot of deep space missions and in fact used on Apollo, for science missions on the moon. It is designed with safety in mind to withstand severe environments, including reentry. There is a process we go through that perhaps Doug can speak more to, where we go through a very sophisticated safety analysis involving the launch vehicle people and DOE and independent reviewers to define the environments and to look at the safety of this device with the environment and to make a judgment as to whether it's safe to go. And we've been very safe using these kind of generators for the past 50 years. And this program is no different in the sense of the process we have used in order to judge its safety and commit to its use.
And let me add that we expect a safe and successful launch. And as you said, we've been flying these power sources for 50 years. And if you have any more details you'd like, we'll get you with the appropriate Department of Energy officials on their power source. Let's go back to Kennedy and to Marsha Dunn.
Thank you. Just a couple of quick factoid questions. I think you mentioned a couple hundred meters above the surface of Mars for the sky crane to start operating. Do you have anything more precise than that? How high will the rover be when the sky crane pops out? Secondly, how deep into the rock or dirt will the drill go when they're looking for samples? And lastly, if you lose a wheel or two, can the rover still go along the surface and do some science? Thank you.
Yeah, if you contact Dwayne's office, I'll get you the actual hard number for the deployment of the sky crane. I don't have it on the tip of my tongue. The drill goes, I believe, 5 to 6 centimeters into the rock surface. And you had one more. Oh, if I lose a wheel, I'm certainly fine if we lose a wheel. This is a situation a little bit better than MER because we actually have. We can release the braking of the motors on this vehicle, and we're not able to do it so much on MER. So we don't have to drag the wheel like we had to do on MER. We can actually freewheel the wheel. We certainly are okay if we lose one. Depending on the terrain, we're probably okay if we lose two. Each of the wheels has its own drive motor, so we have 6 drive motors, and the 4 corner wheels have independent steering motors. So got a lot of flexibility in order to maintain mobility in the event of a motor or gearbox failure.
Okay, folks, what I'm going to do here, we're going to wrap this up. And I again want to remind you of the series of detailed briefings that will be coming out of the Kennedy Space Center on launch week. In summary, right now, we're green across the board to go back to Mars. Please go to www.nasa.gov/MSL. Florida, here we come. Let's go back to Mars. Thanks for joining us.